SwayamPrabha. Digital India. Educated India.
Okay, so today we are going to start a very important as well as interesting part of the course. It's on modeling particle transport in prescribed carrier flow fields. So basically now you have understood the equations governing the transport of single particle. And now we will use that to predict the particle behavior in flows where the carrier phase flow is prescribed, which means that we know the flow field, that is the velocity field, the temperature field of the carrier fields. It need not be constant, but it may vary spatially. But we know how it varies. Even it can vary temporally or spatio-temporally, but that is prescribed. So we don't have to solve the carrier phase equation to get the flow field that is prescribed. So here again the equations are summarized, which we discussed yesterday. Of course, these equations are under some key assumptions. So here we are assuming, for example, we have heavy particles in a fluid, for example, solid particles or liquid droplets in air. So in that case, the ratio of fluid density to the particle density is much less than 1. So we can drop out the terms associated with the undisturbed flow, terms associated with the Bassett history term or the added mass term. So in this case, the momentum equation has only the drag force. Of course, we can introduce a correction factor and gravity. Similarly, here we are considering evaporation or burning of a particle, which is modeled according to D square law. And here we are considering in the energy equation, the heat transfer due to convection and radiation, and as well as the heat transfer due to phase change.
Okay, so there are other assumptions which are inherent. For example, there is no particle rotation, no internal motion within particles. All these assumptions are valid. However, the analysis that we are going to do, it's not restricted to these assumptions. So you can include those additional terms also. So this is for your understanding. We are beginning with a simplified case. Okay, so first we'll look at, so we'll start with a very simple case of particle behavior, or you can say the behavior of a solid particle without any mass transfer in a flow field which is described by a constant velocity of the carrier phase. Then we will bring in further complexity. For example, we'll say, okay, now we will add evaporation. Then we'll consider many particles or a polydispersed system, and also the cases where the particle velocity, the fluid velocity changes spatially and temporally. And like that, we can go on adding further complexities, and you will see that this modeling approach gives a lot of insight into the physics of the flow. Even if this refers to a case where we have some simplification, and the major simplification is that the carrier phase is prescribed. Okay, so the first problem is like this. So we have a droplet or a particle injected at an initial velocity of V0 into a uniform flow of air. where the air velocity is prescribed, given. Find the distance and time corresponding to particle velocity equals to 99% of the air velocity. Neglect gravity and droplet evaporation. Okay, so the scenario is like this. So how do we proceed first of all? So in this case, there is no mass transfer, so and no energy transfer as well. This is isothermal flow. So we have to consider only the momentum equation. So this is what you have. But in the momentum equation, so you see we are using this simplified version of the momentum equation. Okay. So here we have already incorporated drags, Stokes drag law. So we have already assumed that the Reynolds number is far below 1. So that is an inherent assumption. For simplicity, we are doing this. So this is the momentum equation, and because here the question is to find the distance that the particle needs to travel before it reaches 99% of the air velocity. So we have to consider the definition of velocity, okay, or the kinematic. So here x refers to the distance covered by the particle from certain reference location. So this is x. So if it is easy to solve equation 1 and through separation variable as shown here, and then we can integrate. So here the integration is from some velocity, initial velocity v0 to v. For time, which starts at 0 to some time t, and that is how we get the expression for the velocity of the particle. So this is how the particle velocity would vary with time. So here we see that we have an exponential term. We can quickly check if the solution is correct or not just by putting t is equal to 0. Then we get v is equal to v0, t is equal to infinity. We will get this as u infinity. So this means that after a long time, the particle has to reach the velocity of the carrier phase. So now to find the time that we need to reach this velocity, or 99% of the carrier phase velocity, we can find that by putting v is equal to 0.99 u infinity, and you get an expression like this. However, if you look at this expression, here we have the ratio v0 by u infinity. Okay. Now, if v0 exceeds u infinity, will this term be valid? No. So, what should we do? What is the problem here? We haven't made any assumption as of now on the initial injection velocity of the particle, whether it is less than the carrier phase velocity or more. But we have found this expression, which is not valid for particle velocity more than velocity of the carrier phase. So what will happen initially, what will happen in these two cases? In the first case, the velocity of the particle is less than the velocity of the carrier phase. So what will happen to the velocity of particle with time? It will increase. On the other case, it will decrease because the drag force will be negative here. Okay. So this will be more clear if we look at the trends. So if you just plot this here you see that if particle velocity is less than carrier phase velocity, it increases. On the other hand, if it is more than the carrier phase velocity, it decreases. However, is this question valid first of all when you have particle velocity more than velocity of the carrier phase. From this plot, what do you see? Is this question valid? So, if the particle velocity is more than the velocity of the carrier phase, then particle will reach the velocity of the carrier phase after a long time, but it cannot go below that. So, this question itself is not valid. So, it can be made generic by saying that, okay, you reach a velocity which is 1% plus minus 1% of the free stream velocity. So, here it should be 1% more than the carrier phase velocity. So, if you do that, then you get this expression. So, you see the expression does not change apart from this change in the denominator. Okay. Now, so here we found the time required, but how about the distance covered by the particle in this time? What shall we do? If we want to find out how much distance the particle covers in this time, then we need to integrate this equation. So, we can put just this expression for velocity here and just integrate it, and you get an expression like this, where this is valid for this condition, and you have this when the particle velocity, injection velocity, is more than the carrier phase velocity. So, you see that here we have two parts. The solution tells you that you have two parts here. So, if we consider some specific examples, then if we put V naught is equal to 0, so you have a flow, imagine, and you release a particle from 0 velocity. So, you just put V naught is equal to 0 here, and then it is easy to see that the time required to reach 99%, oh sorry, so time required to reach 99% of the fluid velocity is basically around 5 times the tau d. What is tau d? It is the relaxation time. So, it scales with the relaxation time, and the distance traveled by that time is equal to velocity of the carrier phase times the response time multiplied with 3.6. So, you see that the distance traveled scales with this parameter. Okay. Similarly, if I put V naught is equal to 2 infinity, I have to use this equation now. You cannot use this equation for this case. Then we get values like this. Now, when we have stagnant condition, so now imagine you are injecting a particle in stagnant air. Again, the question is how long it will travel before it stops. Why should it stop? Due to drag. Okay. So, in that case, the air velocity itself is 0. So, if you directly put here u infinity is equal to 0, you will get term which are not defined. So, if you put, for example, u infinity is equal to 0, then this will be infinity and this term is 0. And this happens again because of the way we have defined, or we have posed the question, because u infinity itself is 0. Okay. So, it makes more, and the particle velocity, initial velocity, is more than the velocity of the surrounding phase. So, the question should be how long it will take for the particle to reach, let us say, 1% of the initial injection velocity. Okay. So, you can solve the equations the similar way and integrate considering this. So in that case you will get this answer. Okay. So this is the most basic case, okay, where we could predict the distance traveled by the particle before it stops. Next, we can make it more complex. Now imagine the particle is evaporating. So if the particle is evaporating, then how long it will travel before it stops? So that brings us to the next problem. So here the question is, find the distance traveled by the droplet prior to complete vaporization. So there can be two different reasons that governs the distance traveled by the particle before it stops. First one is drag itself. So if the drag is high, it is possible that the particle would come and stop and then evaporate there itself. Second case, the particle size itself reduces. So the particle stops because it has evaporated. Okay. So in that case, how do we find this distance? So this is the next level of complexity. So in this case, what do we need to do? We have to consider the momentum equation as well as the mass conservation equation. So you see, we are using the d square law here directly, because here the interest is on size change rather than the mass transfer rate. Okay. So you write these two, and here again the variable is d. So because now the particle size is changing along with the distance, so we can express the result either in terms of particle size or in terms of x. So by combining, so now we can combine these two equations, okay, and we can write it this way. So dv by dd square is equal to u infinity minus v divided by the particle relaxation time. So now this is a main difference with respect to the previous case. For the previous case, the particle relaxation time was constant, but now that itself varies as the particle reduces, particle mass is reduced. So then we can integrate this, okay, and we can get this expression here. So you see that now the velocity of the particle depend on the ratio of the particle size to the initial size of the particle as well as the initial slip velocity. So here interestingly this ratio comes up as an exponent to the normalized particle size. What is this ratio? Here we have Td naught, which is now the droplet relaxation time based on d naught, and this, what is this? This is droplet vaporization time based on d naught. So what is the droplet vaporization time? How do we calculate droplet vaporization time? This is basically equal to, okay, so here it is assumed that Kv is constant. Is Kv constant actually? Anyone remembers the expression? So Kv, or the evaporation constant, is given by this expression, which is a constant if we are considering evaporation under stagnant condition. But if there is some relative velocity, ideally here we should we should bring in the Sherwood number. So now is it a constant? The answer is no. Why? Because the Sherwood number itself depends on the particle size. Or if we use some correlations for Sherwood number, typically it is expressed in terms of Reynolds number and Schmidt number. So Reynolds number itself is changing. But in this case, we have assumed that this effect is absent. That is, you have pure diffusive mass transfer. Okay. Because we want to analytically solve these equations. Now, if we solve this, we get this expression, and now we can plug in this expression here. So here what are we doing? Because our ultimate interest is the distance, so now I can divide equation 3 with equation 2, and I can express this as dx by dd square is equal to v minus kv. So now the expression for v can be used here, and you get this equation. Okay, still this equation can be solved, because here we can solve this through separation variable again. So if you solve this, and what should be the limit for particle size? So if you see, if we bring in this term here, so then on right side the only variable is particle size. So that we can give limit for particle size from d naught till 0, till it evaporates, and accordingly we get the expression for the final distance travelled by the particle is equal to carrier phase velocity times the vaporization time based on the initial particle size, minus the slip velocity divided by 1 over v naught plus 1 over tau d naught. Okay, so this we get this interesting expression which tells us that the distance travelled by the particle is governed by both drag and evaporation. Now, which is important? Drag is important or evaporation? That depends on the relative magnitude between these two parameters, relaxation time to droplet vaporization time. So we get this expression. Now imagine if the droplet evaporates slowly, then what will happen? The time scale for vaporization is much more than the time scale for the particle relaxation, or it is much more than the time scale of mass transfer is longer than the time scale for momentum exchange. So this means that the particle would quickly it will adjust with the flow velocity. Okay. So then we can drop out this term here, and this can go up, and considering that anyway this is larger than this, so we get the distance travelled by the particle is equal to u infinity tau v naught plus v naught tau d naught. So considering that this time scale for vaporization is longer, okay, and if we assume that okay the u infinity and v naught are comparable, then this is basically we can say that this is controlled by vaporization mainly. So the vaporization process will control how long the particle would travel, because it has reached equilibrium with the surrounding, that is, it has reached the momentum balance with the surrounding quickly. So now it is controlled by evaporation. On the other hand, if the droplet evaporates much faster, then we get this, that is the distance traveled basically equal to V naught times. So here the vaporization is governing, is completely governing the particle, the distance traveled by the particle, because it is vaporizing so fast. Let's say you inject a droplet into a combustion chamber which is maintained under supercritical condition. So it will evaporate very fast. Okay. So in this case, the carrier phase flow does not influence the distance traveled much. Okay. Now this is also one interesting case, particle evaporation or droplet evaporation under stagnant air condition. This is relevant to transport of the respiratory droplets, for example. Okay. Mostly we don't have a strong co-flow, though it may be present. So in this case, if we simply put u infinity is equal to 0, we get this expression. Okay. So in that case, the distance traveled, obviously it is proportional to the injection velocity, but apart from that, these time scales also influence the distance traveled. Not only that, it will affect its trajectory also, that we will see. Okay. Now, how do we model transport of polydispersed particles? So in this example, we are considering droplets, though it is again is not restricted to droplets. So here again the assumption is that the continuous phase is specified, and here we know the inlet mass flow rate of the liquid phase. So the mass flow rate or injection mass flow rate of the mass injection rate is known for the liquid phase. And also we will assume that the characteristic droplet size is known. That is, here we have droplet size distribution is specified. So if you remember, we had discussed this. So how do we specify droplet size distribution? We have to rely on some model which agrees well with the experiments. Let's say you have taken measurements of respiratory droplets, measurement of particle size, and that shows you that you have that fits well to Rosen-Ramlet distribution or log normal distribution. So how do you prescribe that? Scale parameter, spread parameter. Scale parameter means some kind of characteristic particle size you need to know. For example, you know SMD, VMD, AMD, some characteristic size you know, and then the spread parameter. So if you specify these two, then you are specifying the size distribution. So here we assume that the size distribution is specified. Now, how do we calculate the droplet injection rate? What is droplet injection rate? That is how many droplets we are injecting per unit time. Because now here we don't have a single particle system, we have a multi-particle system. And not only that, the system is polydispersed also. That is, you have, in the case of a spray, for example, you have large number of small particles and low number of large particles. Okay. So we can estimate the injection rate by the following. So this is the rate of injection of the liquid. Now this is equal to the number of droplets what we are injecting per unit time, let's say per second. Then this is the, okay, here the term rho d should also come, and this is the mass of individual droplets. But if you remember the expression for VMD, so what is VMD? Volume mean diameter. Okay. Now what is volume mean diameter? This is a representative droplet size such that the mass or volume corresponding to that size times the total number of droplets is equal to the total mass of all droplet or total volume of all droplet, and that is what we are using here. Okay. So because you know the size distribution, you can calculate what is VMD here. Okay. Either you can calculate VMD if you have the experimental data, or else if the particle size distribution is prescribed, that is the continuous distribution is prescribed, still you can calculate the VMD. And once you know VMD, you can use that here. So this bracketed term refers to volume of each particle. So now this is mass of each particle times the number of each particle. So from here, because this is known, you can calculate what is the rate of injection of particle. Okay. So once you know this, then you can use it in your model. So for example, you know in 1 second you are, let's say, injecting 1000 particles. So now in your model, if you want to vary a time step by, let's say, 10 millisecond, then you know how much you should inject in 10 millisecond, because you know how much you have calculated how much it injects in 1 second. Okay, so that is how you bring in this feature. And also we will assume that the droplet size or particle size velocity correlation is known. This means simply that you know the particle velocity as well. Apart from particle size, you know particle velocity also. So if this correlation is given, for example, let's say I tell you that velocity versus particle size is a linear trend. You have a linear trend and this trend is known. This means that you know what is the initial velocity of particle of a given size. And also we assume that the initial droplet temperature is known. Okay. For example, let's say if you are considering transport of respiratory droplets, you can very well assume that the initial temperature is nearly equal to 35 degree. Okay. It may not be easy to prescribe all these parameters for all cases. Okay. But through this you understand how do we, through this simplification, you understand how do we develop a model. So that is the reason why we are making some assumptions. Okay. So now we will look at an interesting example. That is, how do we predict the length of a liquid rocket propellant combustion chamber? Okay. How we can use whatever we have learned so far to make this prediction. So here also we are making some assumptions, and one of the assumption is that in this combustion chamber, temperature and pressure are constant, because the specifically in case of liquid propellant combustion chamber, the temperature, I'm not talking about the initial stage, but when it is running under steady state, the temperature and pressure are typically under supercritical condition, and they are very high, and pressure does not vary much, okay, along the length of the combustion chamber. Okay, there will be some drop due to viscous drag, obviously, but we can neglect that conveniently. And then also we can assume that the temperature does not vary much because it is already at high temperature. So what is the question? The question is, here the liquid injection rate is known. Also, we know the gas injection rate. So here you imagine you are injecting some liquid droplets as well as gas. Okay, here we assume that that is air. Okay, then as I said, the temperature and pressure does not vary and it's constant throughout. And also here we are assuming that the droplets burn right from the beginning. This means that there is no droplet heat up period. Okay, and there is a flame around the droplet right from the beginning, which is also justified because again the temperature is so high. Okay. So, and also we can make equilibrium vaporization or equilibrium vaporization assumption here, though here we have to use the droplet burning rate rather than the vaporization rate. So you have to use the model for droplet combustion, but anyway that does not matter, only the kV value is going to change. And also because of this, the parameter kV also can be assumed constant. Okay, but before that, yeah, so we have to look at a few other things. Because the temperature and pressure are constant, so the density of the gas is also constant. And now we can do a mass balance. So how do we do that? So first, what is the mass flow rate of air which enters the system? That is rho c, UC, O refers to the condition here at the inlet times the area, plus what is this? This is the number flux, that is number of droplets that we are injecting per unit area per unit time. So this is nothing but what we have just discussed, n dot divided by area, that's all. So number flux times area, this is the droplet injection rate times the mass of individual droplet. So basically here you have mass of gas that you are injecting, here mass of droplets. So now at certain location from the beginning of the combustion, you have the mass flow rate of the carrier phase basically equal to rho c, because here we have assumed that the density is constant, air density is constant. So I can use rho c, UC, that is the gas velocity at that location times area, plus again number flux times the mass. But here the particle size has changed. Okay. So here you see that the number flux remains constant. So that is the number of particles that you are injecting, that remains constant. The particle size may be reducing, but the number remains constant. This means that you have made an inherent assumption that there is no particle collision. If particle collision takes place, then the number would change. Okay, and also there is no particle interacting with the wall of the combustion. So these assumptions are inherent. So if we use this, we can simplify this and write the gas velocity in terms of particle size. So by rearranging this term, we can show that the gas velocity is equal to the initial velocity of the gas plus 1 plus phi times 1 minus dq by d naught q. So what is phi? Phi, if you see this term, this is this part you see. This is the initial mass flow rate of the liquid what we are injecting. So by we can show that. So if we multiply this with the gas velocity and divide and multiply with ACO, UCO, okay, then it is possible to show that basically this term is equal to the ratio of mass flow rate of the liquid to mass flow rate of the gas. Okay. So what is this? Because the area is constant, I can write also this as mass flux of dispersed phase to mass flux of carrier phase. And that, what is that? That is loading. We have defined it earlier. Concentration and loading. Okay, and you get this expression. So now what does this tell you? What happens to the gas velocity? So if I put d is equal to 0 here, this means all the droplets have evaporated. So if all the droplets have evaporated, then this term, what will I get? The final exit velocity so what do we see here is that the carrier phase velocity is now not constant. The carrier phase velocity is increasing simply because of mass conversion. The droplets are getting converted to the gas phase. Okay. So here you see we are not considering any combustion reaction calculation. Okay. Only by mass balance we are showing that actually the gas velocity would increase. So now you think of your equations. So in the previous examples, the carrier phase velocity was always constant, but now the carrier phase velocity is increasing, but that itself is a function of size only. So if you see, the carrier phase velocity is only a function of size. So this will help us to solve the equation again analytically and finally find the length scale of the combustion. So why we are particular from a practical point of view, why are we particular about the length scale of the combustion? Because if you see, if you make the combustion length very long, so obviously all droplets would evaporate at some point of time, right? But in this case, you want to minimize the combustion chamber length because it is for space application. You need to reduce the weight. So now, can we predict the length? If I know that, okay, this is my mass, this much liquid I am going to inject per unit time, or the mass flow rate of the liquid, what will be the combustion chamber length, and which factors influence that, apart from the basic parameters like the injection. So if you increase the injection rate of the liquid, then obviously you may have to increase, but we will see what factors actually govern the length scale of the combustion. Okay, so we'll stop here. We'll continue this in the next class.